In this video, I'm going to cover techniques for differentiating trigonometric functions. In order to be able to actually move on to the differentiation of trig functions, you need to be familiar with at least the following. You need to know how to break down a function into two simpler functions known as composite functions. You need to be familiar with the product rule, the quotient rule, and some trigonometric identities. So the first thing I'm going to do is quickly cover these four concepts really quickly. So I'm going to start with composite functions. Here you can see y is equal to x plus 2 squared. Y is a function of x. And the idea is to break down break down this function into two simpler functions. So the approach here I've used is to first let a variable u equal x plus 2, and then of course based on that y is equal to what? Basically, if you carry out a substitution, so you replace x plus 2 with u here, you get y is equal to u squared. So this equation, y is equal to x plus 2 squared, has been broken out into two equations, two functions. U is equal to x plus 2 and y is equal to u squared, because y is actually x plus 2 squared and x plus 2 is u. And the benefit of this is that it makes the differentiation of this function easier. Now, y is equal to x plus 2 squared. If you wanted to differentiate it, one way would be to expand this. So you pretty much carry out the expansion of x plus 2 squared, which is laborious when you have a simpler approach where you can break it down into two simpler functions, and then to find the derivative of y with respect to x, so dy dx, you just have to find the derivative of y with respect to u, and then multiply the result by the derivative of u with respect to x plus, with respect to x. It's a much simpler process, and I'll just quickly do it for this example. So in this case, we're looking for dy dx. You're given this function, you want to find dy dx. What is dy du? Well, since y is u squared, dy du is 2u. And u, because u is x plus 2, du dx is simply 1. So dy dx, which is dy du times du dx, so 2u times 1 is 2u, and u is x plus 2. So it's 2 into x plus 2, which is equal to 2x plus 4. It takes less time than actually, carrying out the expansion and then differentiating. In this example, this function needs to be expressed in terms of two simpler functions, and the ultimate aim is to simplify the differentiation of the function. It's important to note that sine squared x is the same thing as sine x squared. So cos squared x is the same thing as cos x squared. So y equals cos squared 4x is the same thing as y equals cos 4x all squared. So what I'm going to do, I'm going to say let u equal cos 4x, so that y is going to be equal to u squared. And then if I was interested in differentiating, so finding dy dx will be equal to dy du times du dx. So in other words, I'll just have to differentiate this dy du, which is 2u, and then find du dx, and we're going to learn how to differentiate trigonometric functions. But the whole point here is just breaking down a function like this into two simpler functions which can easily be differentiated. The product rule is also important. You'll have some cases where you will have to differentiate a function which is made up of the product of two trig functions, and it's really simple. If you have, in the case we have y is equal to the product of u times v, where I have u as a function of x and v as a function of x, which is the same thing as y is equal to uv. If I ignore making it clear that, if I don't make it clear that we use a function of x, y is equal to uv. U is the first function, v is the second function, and dy dx is equal to u times dv dx. So it means the first function times the derivative of the second function with respect to what we're differentiate, well, x, plus the second function v times the derivative of the first function with respect to x. So that's the product rule. Easy to use. I'll quickly go through an example here. So we have to determine dy dx. Y is equal to the product of two functions. The first function is just x, so u is x, and the second function is x plus 2 squared. So v is x plus 2 squared. So you can see that y is equal to uv, the product of two functions of x. So the product rule says that, and by the way, y prime, the notation used here, in case you haven't come across it, y prime is the same thing as dy dx, v prime is the same thing as dv dx, u prime is the same thing as du dx. So I'm just going to use the prime notation because it's easier to write y prime than to write dy dx. So if I want to find dy dx, which is the same thing as y prime is uv prime plus vu prime. So I need to know v prime, I need to know u prime. Well, if u is x, what's u prime? What is du dx? Differentiating x with respect to x gives 1. What about v prime? Well, differentiating this expression with respect to x gives what? Well, from the top of my head, it's 2 into x plus 2. To show you the exact process, in case you're not familiar with differentiating this, well, you can think of this as y is equal to x plus 2 squared. And you can say let u be x plus 2, so that y is u squared. So I've broken down this function into two functions, so that dy dx is going to be dy du times du dx. dy du is 2u, and u is 2x plus is x plus 2, so that's 2 into x plus 2, and then du dx is simply 1. The result is 2 into x plus 2, and that's what I have here. I expect you to be able to differentiate this function, so this is just there for the workings. Apologies for using the same notation, as in using u and well, having two u's. Just consider this as a side rough working. But moving on, we're pretty much done because we now know that y prime is simply u times v prime, so x times 2, so x plus 2 plus v times u prime, this times 1, and anything times 1 is itself. So in short, what we have is 2x into x plus 2 plus x plus 2 squared, which could be simplified further, but the whole point has been made. We've used the product rule to carry out a differentiation. The quotient rule is useful when you're differentiating the quotient of two functions. So anytime you have an expression of the form y is equal to u over v, so a function divided by another function, the quotient of two functions. So anything of the form y is u over v, the dy dx is given by this. So y prime is dy dx, u prime, just to remind you, is y prime is dy dx, u prime is du dx, v prime is dv dx. So once you remember this formula, you can actually differentiate functions of this form. So let's just move to an example. In this case, we have the quotient of two functions. I mean, y is equal to the quotient of x and x plus 1. So if you think of the form y is u over v, u is x, and v is x plus 1. Now from the formula, you know that you need u prime and v prime. You already have v, we already have u. V squared is just multiplying v by itself. So when you define u prime and v prime, that's always the first step. What's u prime? Du dx. Well, we're differentiating u with respect to x. That gives 1. V prime, we're differentiating v with respect to x. So derivative of x plus 1 is v prime with respect to x. So x plus, that gives 1 as well. So according to the quotient rule. Y prime is equal to v times u prime, which is x plus 1 times 1, minus u times v prime, which is x, divided by v squared, which is x plus 1 squared. This is simply, well, if you drop the bracket, so this gives 1 over x plus 1 squared. So dy dx is, this is dy dx. And that's just an application of the quotient rule. Finally, you need to be comfortable with common trigonometric identities. The complex ones will usually be given to you in an exam, but these ones are easy enough to remember and quite useful. The cotangent, also known as cot, cotangent of x is simply 1 over tan x. The secant of x, simply 1 over the cosine of x, secant and cosine. And the cosecant of x is simply equal to 1 over sine x. This is useful to remember. And of course, sine squared x plus cos squared x is equal to 1. Another useful identity to remember.